Hello, everybody. Yesterday in class, we went through a few examples in section 4.1, and then we started looking at second derivatives and graphs. So we went through the handout, we talked about concavity, talked about concave upward, meaning the derivative is increasing, concave downward, meaning the derivative is decreasing. We defined the second derivative as the derivative of the first derivative. And since your concave upward if the first derivative is increasing, in the summary box on the bottom, down here, well, if the first derivative is increasing, that means the second derivative is positive and your concave upward, and if the first derivative is decreasing, the second derivative would be negative. That gives you concave down. And then we also talked about finding the partition numbers for the second derivative. These partition numbers, where the second derivative is 0 or undefined, are the values where the second derivative possibly changes sign, i.e. the concavity changes from up to down or down to up. Okay. And then we did an example. We looked at f of x equal, in example 1, we looked at f of x equals x cubed. We determined the intervals of concavity, where is it concave up and down. We sketched a rough sketch of the graph. And then what we did is we went on to define what are called inflection points. That's a point on the graph of the function where the concavity changes from down to up or from up to down. And theorem that an inflection point can only occur at a partition number. Okay, so what you do is, again, you find those partition numbers where the second derivative is 0 or undefined, and those are the only possible places where the concavity can possibly change. And then in this image down here, it's a picture of 4 graphs, some examples of where you have, an increasing function in your inflection point, and the graph changes from concave up to concave down. And there's another way that can happen is part C. You could have a decreasing function that changes from concave up to concave down. And then there's some other possibilities as well for changing from concave down to concave up. Okay, and let's see. We went through example 2. We found the inflection points of x cubed minus 9x squared plus 24x minus 10. We did an example talking about the derivative, given the graph of a derivative of a function. We used the derivative to find intervals of increase, decrease, intervals of concavity, and drew a sketch of the graph of f. And then where we started off yesterday, on Tuesday, we started looking at curve sketching, and this is the strategy for sketching a graph of a curve. And this is the first version. In section 4.3, we'll be looking at some more complicated functions, basically just rational functions that might have other information like vertical asymptotes, horizontal asymptotes, things like that. Now, I'll go through the last 3 examples from the handout. So, the procedure in this graphing strategy, it's really a 4-step process. The first 3 steps are just analyzing the original function, the derivative, and the second derivative. For the original function, you can find the domain in the x and y intercepts. Step 2 would be analyze the derivative, so find the partition numbers for f prime and the critical numbers. Construct a sign chart, which would allow you to find intervals of increase and decrease, and then tell you where your local maxima and minima are. And then step 3 would be analyzing the second derivative. You find the partition numbers for the second derivative. Again, construct a sign chart, pick some test values on those intervals. That allows you to determine the intervals on which you're concave up and concave down, and also allows you to find the inflection points. And then with all that information, you can plot the x and y intercepts. You can plot all the inflection points and the local maxima and minima, and then use your sign charts and all your information from the first 3 steps to draw a curve that goes through those given points. And when you're done, your sketch is going to look awfully close to the actual graph. So what we were able to get through on Tuesday the 15th was this example 4. And what I'll do here is I think I'm just going to spend my time going through example 5 and then also do example 6. Hopefully everybody watches the video and is ready to come with questions on the homework in class on Thursday. There may or may not be a video on Friday to get us started on the next section. Okay, so let's take a look at example 5. So I need to make some room. Okay, and let me increase the size of the document so that we can all see it slightly better. Okay, and let's go ahead and get started on this one. Okay, so our function f of x is 3 times x to the 2/3 minus x. We're going to find all the pertinent information, so information on the function itself, the first derivative and the second derivative, and then we'll use all that given information to draw a pretty darn good sketch of the graph. Okay, so what we'll do is we'll do this again stepwise. So step 1. Okay, this is going to be to analyze the original function. Now, the two terms both actually have domains, so the first and second term up here, you can actually plug any x value you want, positive, negative, or 0. Right? There's no problems plugging in anything into the x over here. And the x to the 2/3, since you're squaring the input first and then taking a cube root, there's no issues plugging anything you want in for x. So we'll identify the domain, which is going to be all real numbers. Okay. And then we can find the y-intercept and the x-intercept. So the y-intercept that's the value of the function when x is equal to 0. So notice if I do look at f of 0, we get 0. That means the origin is a point on the graph. It's also the x. It's one of the x-intercepts, and it's also a y-intercept. Okay, and then the x-intercepts, what we're going to have to do is we're going to have to set the function equal to 0. Okay, and then we will solve that for x to give us the x-coordinates of the x-intercepts. Okay. Now factoring this, you can always factor out the lowest power of x. So I'll have an x to the 2/3, and then inside what I'll have left over is going to be minus an x to the 1/3. Okay. So setting each of these factors equal to 0, and then solving for x gives you, well, the first one, if x to the 2/3 is equal to 0, you can raise both sides to the 3/2 power, and that'll give you that x equals 0. And then over here in the second equation, if you add the x to the 1/3 to the other side, this is going to give you, well, we already knew x equals 0 was an x-intercept, which also is going to end up giving us a y-intercept as a repeat. And then if you cube both sides on the right equation, x is going to equal 3 cubed, which equals 27. Okay, so that gives me the domain x and y intercepts, and that's all the information that we require on the original function itself. Okay, so now it's time for step 2. Step 2 would be to analyze the first derivative. So we can go ahead and find f prime of x, which would be 3 times 2/3 x to the minus 1/3. So that was the power rule on the first term. And then the derivative of minus x is minus 1. And then I can go ahead and simplify this function. 3 times 2/3 is going to give me I'll write it this way. It's really 2 over x to the 1/3 minus 1. Okay, so the 3 times 2/3 is 2, and then 2 times x to the negative 1/3 is the same as 2 over x to the positive 1/3. And then I can go ahead and get a common denominator. And this will equal 2 minus x to the 1/3 over x to the 1/3. Okay, so there's my derivative f prime of x. Now, f prime of x, we have to find out where it is equal to 0 or undefined. So it's 0 or undefined when either the bottom equal to 0 or the numerator 2 minus x to the 1/3 equals 0. And when you solve both of these, you're going to get x equals 0 for the first equation, and you're going to get x equals, well, let's go ahead and solve this one right here. This would lead me to x to the 1/3 equals 2, which implies that x equals 2 cubed, which is 8. Okay, so those are going to be your critical numbers, right? Those are partition numbers, but the domain was all real numbers. So that means those are the critical numbers. So those are the places where we possibly have a local max and min. Now we can make our sign chart for the first derivative. I will put down 0 and 8. Excuse me. And then we will test the sign of the derivative. Now you can pick some test values for yourself, but when we plug in minus 1, you're going to get a positive in the numerator and a negative in the denominator. So the sign of the derivative to the left of 0 will be negative. Right? That means the original function is going up, it's increasing. And then if you pick something like positive 1 and plug it into the derivative, you're going to get positive values. And then if you pick anything larger than 8, say 9, or actually, how about I pick something with a cube root? If I try something like 27, 2 minus 27 to the 1/3 is negative. The 27 to the 1/3 in the bottom is positive, so the derivative will again change signs. So we are, oh, I actually made a mistake here. If the derivative is negative, whoa, Chris. If the derivative is negative, that actually means the function was decreasing. It's increasing on this interval, and then it's decreasing for values of x larger than 8. Okay. And then that means that you also know that f of 0 equals, well, I guess, yeah, you plug 0 into the original function. Okay, so look back, f of x is 3 times x to the 2/3 minus x. If you plug in 0, you get 0. That's going to be a local max. Sorry, I'm just backwards today, folks. That's going to be a local min, because the derivative changed from negative to positive. And then f of 8, which is approximately, or which is identically first, equal to 3 times 8 to the 2/3 minus 8. This equals, oh man, and I ran out of room. Let me rewrite this, y'all. So actually, f of 8, which is 3 times 8 to the 2/3 minus 8. This equals, well, 8 to the 2/3, you can cube root 8 first to get 2. 2 squared is 4, times 3 is 12, and 12 minus 8 is 4. This is a local max, because at 8 the derivative changes from positive to negative. Okay, so there's all our pertinent information about f prime, and when I finish step 3, I'll rewrite all the information we found from steps 1, 2, and 3, and then we'll go ahead and sketch a graph. Okay, now it is time to analyze the second derivative. So recall, recall on the previous page what we found out was that f prime of x is equal to we found it to be, well, actually, I'm not going to take the simplified version, but let me actually write down the derivative before we simplified. It was 2. Sorry, I just got disconnected from my desktop again. Sorry for all this malarkey. Okay, so the 2/3 came out front. You got 2x to the minus 1/3 minus 1, which is equal to, and then we simplified and got 2 minus x to the 1/3 over x to the 1/3. Now, if we're going to take a second derivative, I'd rather not use the quotient rule, so I'm actually going to use the derivative in the form we obtained first. So the second derivative, f double prime of x, is going to be 2 times negative 1/3 x to the next lowest power, which would be a minus 4/3. And then simplified, this would be negative 2 divided by 3x to the 4/3. And this equals 0, or is undefined, only, and I think it's pretty easy to see, when x equals 0. I ran out of room. Let me just rewrite that a little smaller. So, or, I'll just write it this way. It's 0 or does not exist, same as undefined, when x equals 0. So that's the only partition number for the second derivative. Now, other than at 0, the second derivative, negative 2 over 3x to the 4/3, this is less than 0 for, well, as long as x does not equal 0. So the second derivative is always negative. So even if I was to make our typical number line for the second derivative, put my partition number of 0 on there, you would see negative signs on the both sides of 0, meaning where, well, let me write it in words. We are just concave down and concave down. And I don't know why I didn't write the O there. Okay, and then also, since it's at our partition number, the concavity doesn't change. There are no inflection points. Okay, so this graph is always concave down. Okay, so here's all our pertinent information. Step 1, we found the domain was all real numbers. X-intercept are 0, 0, and 27, 0. Y-intercept is also the origin. Step 2, we found we're increasing on the interval from 0 to 8 and then decreasing elsewhere. There were no inflection points, and we also found that it was concave down everywhere except for at 0 the second derivative didn't exist. So again, the function is essentially always concave down. Okay, now we're ready to sketch a graph. So one thing I need to do, I need to make sure that my x-axis extends in the positive direction until I at least have 27 units. Oh, I also forgot to write down another piece of information. I forgot to write down f of 0 equals 0 is a local min, and f of 8 equals 4 is a local max. Okay. Okay. And then now what I'm going to do is I'm going to sketch a graph down here. So again, I think on the y-axis, since 0 is a local min, 4 is a local max, we don't really have to extend that many units in the vertical direction. Okay, but we do have to extend in the positive x-axis quite a ways. So I'll just go ahead and, forgive me for a second, because I can just not draw a perfect graph here. I don't think I need much of a direction in the negative x-axis, but what we'll do is we'll go 1, 2, 3, 4 units up, and then I'll go in, like, let's see, how about I go in 2s on the x-axis, although I need a lot of tick marks, so I think what I'm going to do is go by 4s. 4, 8, 12, 16, 20, 24, and over here at 28. Okay, so what we'll do is we'll plot our intercepts. We have the origin. Let me maybe switch colors to, I think red will work. So we got the origin as a point. Somewhere over here we have an x-intercept at 27, 0. We know that at 8, f of 4 is a local max. We know the origin is a local min. And then what the function's going to do is it's increasing from 0 to 8, but remember it's always concave down. Okay, so the function's always concave down. It is decreasing from negative infinity to 0. Okay, now here's one thing that's kind of interesting, because the function's always concave down. To the left of 0 you're decreasing, but to the right of 0 you're increasing. So what that really means is the only way you can be concave down and decreasing is if you have that shape, and the only way you can be concave down and increasing is to the right having this shape. Okay, so it's concave down from 0 to 8. Okay, we also know it's increasing. You have that local min at the origin, and then when you get to 8, 4 is the local max. Now the function is still going to be concave down, but it's going to switch to decreasing, and you're going to decrease through your x-intercept. Okay, so the graph is going up to the left, and it is going down to the right. Okay, so there's a rough sketch of the graph of f of x. That's your x, 3x to the 2/3 minus x. Okay, so now, final example, application problem. We're going to talk about point of diminishing returns. So what we're going to be talking about is a function that gives us the monthly sales based on an investment of X thousand dollars in advertising. Now the definition of the point of diminishing returns: the dollar amount X at which the rate of change in sales, so the derivative of sales, goes from increasing to decreasing, i.e. your graph is going to switch from concave down to concave up. This is called the point of diminishing returns. So, and it's also the point at which the rate of change has a maximum value. Okay, so it's where the rate of in the idea of sales here, it's where the rate of change in sales is increasing the most. And then money spent beyond this point may increase sales, but it's going to do so at a lower rate because the rate of change in sales will be decreasing after that point of diminishing returns. Okay, so example. I guess one more quick comment before we do this example. Okay, and that is, I just want to maybe say that the point of diminishing returns X is the value of x, oops, that looked like an alpha, of x such that the second derivative at x equals 0, right? So this x is actually going to end up being a partition number for the second derivative, and it's going to be a place where the second derivative changes from positive to negative, right? So where the first derivative goes from increasing to decreasing. And the first derivative is the rate of change in sales. Okay, so really the point of diminishing returns is just going to be, it's going to end up being an inflection point on the graph of the original function, because it's a place where the second derivative will end up being 0. Okay, so we'll go through this example. We'll find when the rate of change of sales is increasing and decreasing, and then at that point where it changes from increasing to decreasing, that'll be the point of diminishing returns, and we'll plug that value back into the derivative to get the maximum rate of change of sales. Okay, and then what I'll do is I'll plot this function and its derivative into Desmos, and we'll be able to see the connection. Okay, so currently a discount appliance store is selling 200 large screen TVs monthly. If the store invests X $1,000 in advertising, the ad company X estimates that the monthly sales will be given by this function N of X, given right here. Okay, so that's your that's the amount of sales as a function of the amount spent on advertising. Okay. And this number here that they're selling 200 large screen TVs monthly, that's really a distractor value. I mean, it doesn't really tell us much of anything. That amount's going to increase and decrease depending on the amount X $1,000 spent in advertising. So that's a distractor number here. And then the first question, when is the rate of change in sales increasing and when is it decreasing? Okay. Now, pay attention here. It's not when is the original function increasing and decreasing, it's when is the rate of change in sales increasing and when is it decreasing. You have to use the second derivative to determine where the first derivative or the rate of change is increasing or decreasing. So what we'll do is we'll start taking derivatives. The first derivative is going to be 12x squared minus x cubed. Okay, so I just use the power rule on each of those first two terms, and then the derivative of 500 is 0. And then I can take the second derivative, and that's just going to be 24x minus 3x squared. And then for the sake of finding where that's 0, finding the partition numbers, I can factor out a 3x and be left with 8 minus x. Okay. And this equals 0 when x equals 0 or 3. Although we don't really care about 0. Okay, the point of diminishing returns is going to be something between the 0 and the 12 from the domain. So when you come up here and look at the domain, right, we're only really spending between 0 and $12,000 on advertising. And what this really says is the second derivative is going to be 0 when we spend $3,000 on advertising. Okay, and the second derivative is going to be defined everywhere, so the only partition number is going to be when x equals 3. Now you can make a sign chart for the second derivative, and remember this is also telling you where the first derivative would be increasing or decreasing. Now, using your second derivative, 3x times 8 minus x, and again I didn't put 0 down on here because, well, I don't really care. the point of diminishing returns is going to be somewhere between 0 and 12. If you pick something to the left of 3, say positive 1, and plug it into my second derivative, you're going to see that you get a positive number. And then if you plug anything between 3 and 12 into, oops, I made a mistake here. Some of you probably caught this because you're probably even more perceptive than I am at times. Really, 8 was the critical number. I guess I can fix that over here. Okay, so the point of diminishing returns is really going to end up being $8,000 spent on advertising. And then, like I said, if you plug 9 into 3x times 8 minus x, you're going to see negatives. Okay, so based on that, you can get rid of this information on the first and second derivative now. Okay, so the answer to the first question, the first derivative, i.e. the rate of change in sales, increases. Okay, so I don't know where I lost everybody. I forgot to push play and restart the video, but I'll write this down real quick and then erase it. We found that the second derivative was 3x times x, or 8 minus x. And that equals 0, I said, when x equals 0 or 8. Now, your point of diminishing returns is going to be inside of the interval. Remember, we're only spending between $8,000 and $12,000 on advertising, so this 8 down here means we spent $8,000 on advertising. You make the sign chart, and then to the left of 8, the first derivative, well, so the sign of the second derivative to the left of 8 was positive, and the sign of the second derivative to the right of 8 was negative. That means the first derivative is increasing between 0 and 8 and decreasing between 8 and 12. Okay. So what I can say is the rate of change in sales increases on the interval 0 to 8 and decreases on the interval from 8 to 12. Okay, so this means that if they spend between $0 and $8,000 on advertising, the rate of change in sales is going to increase. Okay, and then if you spend between $8,000 and $12,000 on sales, the rate of change is going to decrease. Okay, now what this means, a place where the first derivative or the rate of change changes from increasing to decreasing, i.e. this value of 8 down here, that means that the value 8 or 8,000 is going to be the point of diminishing returns. And then the maximum rate of change in sales, we're going to plug 8 into the derivative. Okay, so let me clear a lot of this information. So again, the first derivative was 12x squared minus x cubed. Second derivative was really 24x minus 3x squared. Okay, and then since the rate of change in sales changed from increasing to decreasing when x equals 8,000, the point of diminishing returns is x equals $8,000. Okay, so that's the point where, again, the rate of change changes from increasing to decreasing, and that also ends up being the place where the rate of change has a maximum value. Right? If the rate of change changes from positive to negative, n prime of 8, which is 12 times 8 squared minus 8 cubed, this is going to equal let's see. Well, for this I'll have to get out a calculator. And I get 256, and then the units here are going to be, let's see, so it doesn't say what the units on the monthly sales should be. I'm just going to assume that it's dollars. So basically the rate of change in sales at that point is going to be, your rate of change of sales is going to increase by $256 per $1,000. And what that really means is that every $1,000 you spend on advertising, you can expect your sales to increase by $256. Now, I'm kind of guessing that really the units on this function in of x should also be in thousands. That would make more sense to me. I mean, every $1,000 you spend on advertising, you would kind of hope that you would get a greater return in sales. So maybe what this means is that your sales are increasing by $256,000 for every $1,000 spent on advertising. Okay, we'll make sure that I'm clear on the units when I'm actually putting questions on tests, and I'm pretty sure that they're clear with what the units should be on the homework. And then last thing I want to do, this video is getting kind of long, I just want to show everybody Desmos real quick. I want to show you the graph of the original function and the derivative. Okay, so here I am on the Desmos graphing calculator, and the graph in red is the sales function. Okay. And the blue graph is going to be the derivative. And what I want you to notice, at $8,000 in advertising, right, to the left the derivative is increasing, to the right the derivative is decreasing. And that also gives you an inflection point right here at 8,1524. Okay, so again, that place where you have a, and also I guess I should say this, right, we knew that the maximum rate of change in sales was this $256 or $256,000 depending on what the units were. And then straight above that, if you look at the graph, just above that point, that's going to give you an inflection point on the original graph, and that's a place where the concavity changes from up to down. And then what happens is that this point of diminishing returns, that's the place where, again, you have a maximum rate of change in sales. Okay, after that point, your rate of change in sales is going to start decreasing. Okay, now that's all I have. Again, 38 minutes was probably longer than I wanted, but I wanted to maybe make sure I explained everything. If anybody has questions, let me know. We'll maybe spend a little bit of time on Thursday at the beginning of class, maybe like 10-15 minutes, maybe going over a question or two. But thanks for tuning in, and I'll see everybody Thursday.